Hello, my name is Frank Ferro. I'm the Senior Director of Product Management at Rambus. I want to thank you for taking the time to listen into the presentation. Today, I'm going to be talking about high bandwidth memory and how that is supporting the growing need for generative AI training. So growth in data traffic continues to stress the infrastructure, and certainly generative AI is a key application that is putting all the need for data. It's amazing. Every time I give this presentation, I think that we're going to see some slowing, but it's quite the opposite. We're seeing more and more data, and all the predictions are not only coming true for data growth, but are certainly exceeding them. And the data centers continue to grow. We now are approaching 900 hyperscale data centers. So those I talked about that in previous talks, and those are coming right on schedule. Also, even in a down economy, we're seeing and again, there's some infrastructure investment slowing, but we're still seeing growth, $10 billion year over year growth from last year. So the investments continue in data center. These are especially by some of the big three hyperscalers. And we just see the pressure continuing, and this need for more infrastructure is going to trickle down into the systems, the semiconductor, all segments of the technology. So if we look more specifically at generative AI, you can see on the right-hand side some of the more well-known and popular language models, and you can see the size of these are just continue to expand. Everyone's familiar with ChatGPT, which GPT-3 was about 170 billion parameters. GPT-4, and I don't know that we've got the exact number, but it's over trillion and a half parameters. So these are growing at phenomenal rates, and you can see other models like the Pathways PaLM are 500 million parameters, and the Megtron natural language is also another 500 million. So these models require intense amount of computing from a processor standpoint. They also require quite a large amount of memory bandwidth. And so the first thing we have to think about is not only just the memory bandwidth. You want to create very efficient architecture. So first of all, you need that compute power, but then how do you optimize that compute power? It's things like how do you maximize your precision, quantization, sparsity, if there's a lot of zeros in the database. So we don't want to just do raw computing, right? We want to look at that compute power and then optimize around it. And it's not just things like GPT that are causing it, but the need for a lot of on-premise equipment is now moving up into the cloud. So you've got these large language models. You've got more and more applications moving into the cloud. And even for generative AI, we're seeing things like you can create you can have your AI create your PowerPoint, right? I asked AI to create this presentation for me, and there are tools that will help with that and help and guide you. Even semiconductor design is using AI. The EDA industry is starting to use AI to guide. So every segment, every industry, whether it's healthcare or technology, we're seeing generative AI is being used and deployed, and people are trying to figure out how to take advantage of it. But before I get too far, I wanted to take a minute to talk about some of these definitions, just in case you're not familiar. And sometimes we talk to people and they're not familiar with these terms, training and inference. So let's define our terms a little bit. So training really is the process of teaching the AI what you're trying to recognize. And in this simple example here, you're showing some images that you're trying to recognize. And the best way to get good results is to put a lot of data and put a lot of data into the models and then train it. And this is how you get the most accuracy. But this is a time-consuming and memory and compute-intensive process. And so you could take days or weeks or even months to train these AIs to get good, accurate results. And so that's the whole process of training, and we'll talk a little bit more about that. And then once these models are trained, inference is really the process where you go to recognize what you've trained now. And this is a less compute intense process, although it's still requires quite a bit of computing. And it's also a more sensitive from a standpoint of price and performance and power, because your inference usually moves out of the data center and out into the network, whether it's at the edge of the network or even in a consumer device. And so the inference is important. And actually, I'm going to be giving a talk later today where we're going to spend a little bit more time on inference. So if we look at what kind of hardware is used for AI today, and it's been predominantly GPUs, and by far you can see the GPUs are still, I've seen 90% of all these training models are done on GPUs, and that's probably not going to change very much. I see a lot of custom processors. That's in the data center. Excuse me, it's not changed much in the data center, but there are a lot of custom processors that are being built and designed, because as good as the GPUs are, there are ways to optimize if you understand specifically what type of AI you need. If you're doing a specific application, say around finance or around healthcare, then you could maybe build a processor that's much more efficient from just in terms of compute and memory bandwidth. So we do see a shift from GPUs into more application-specific processors, and even especially at the edge. And as we move out into the network, then as I just mentioned, where you're more cost sensitive, having a application-specific processor would be the way to go. And you can see over time, predictions are that we're going to see more and more of these custom processors. And we work with a lot of companies at Rambus, and we get to see so many companies are building these processors. So GPUs are going to continue to be strong in the data center, but as we get into more specific AI requirements, we're going to see accelerators and custom devices. And again, these custom devices, we can then optimize both the performance and the memory around that. And we're going to look a little bit more at how we optimize the memory. So what are your memory choices that you have for your AI training system? So these are the common memory systems that are available. And if you've done any work in memory, everyone should be familiar with DDR. That's still the predominant memory that's used in the data center. And that's not changing anytime soon. It's a good low-cost memory. It has great density and perfect for data center applications. But as we look at more bandwidth needs, DDR4 was around 3.2 gig. As you get into DDR5, we're getting much higher speeds. But LPDDR, for example, was already LPDDR4, 4X was at 4.2 gig. GDDR is at 16, and HBM is, we're going to talk about that more, is all the way up now to significantly higher bandwidths, and I'll go into the details of that in just a minute. But as we look out into the marketplace, we see multiple memory systems being deployed for AI, and GDDR and LPDDR, for example, are very good memories that used for AI inference. If you recall, a few minutes ago, I just said, once you've trained those models up in the cloud, now you want to push those out into more application-specific devices, and that's where you're going to have a little bit more cost sensitivity. And GDDR and LPDDR and even DDR are good solutions there. So they're breaking out of their traditional roles where LP was being used primarily in mobile. GDDR is graphics memory, and it's still being used as graphics. But as we look into the training, it's clear that high bandwidth memory is the memory of choice, because it's giving you the maximum amount of bandwidth that you're going to need for some of these training algorithms, training networks. And it's configurable from standpoint, you can have multiple memory stacks. So you get very high bandwidth, but as you can see in this graphic here, this particular graphic, you can see 4 memory stacks. So again, you can expand to significant amount of bandwidth, and even gives you some additional memory density. So let me give you just a kind of a refresher on HBM3. And again, the industry's been moving relatively fast. It seems like HBM3 was just announced back in January, but about a year and a half, and already most systems are moving to HBM3. So if you recall, some of the key advantages, new features of HBM3 was it does raise the data rate up to 6.4, so basically doubling it over HBM2E. They did keep the 1024 bandwidth. So again, HBM memory is about going wide and slow, and that's the idea, is to try to keep the relative pin rate as low as possible for power management, but then give you the most bandwidth. So now you're getting up to 820 gigabytes per second of memory bandwidth, which is quite significant at 6.4. And HBM's even already moving faster, and I'll talk about that in just a minute. It doubles the number of memory channels from 16 to 32. So again, helps flexibility as you're doing some of these networks. Having more granularity in the channels is going to give better memory efficiency. You also get more density in the stack, so you're getting up to 12 high DRAM stacks. Again, I may have skipped over this in the last slide, but if you look, HBM is still basic DRAM technology, but it's taking that DRAM technology and stacking it into a 3D configuration. So now you're going to get, with HBM3, up to 12 high stacks, and even moving into 16 into the future. And with that comes more device density. The architecture is still 2.5D. But one of the other things is, as we're increasing the speed with HBM, you also are conscious of the power and the voltage. And again, HBM is put into a very small footprint, very close to an SoC. So power management is critical. And so one of the things that HBM3 did was to reduce the I/O voltage down to 0.4 volt signaling. So even though we're bringing the speed up, we're trying to keep the I/O power equal or even reduced. So you can see here the trend for HBM, and again, the standard's been moving at a incredible rate for DRAMs, and that pace has really been driven by these hyperscale data center customers, where they just can't get enough bandwidth. And so HBM2 came out, is originally like as a graphic solution, very quickly moved into other applications in networking, and then as AI started to take off, as a preferred solution for AI training. And then in 2018, HBM2E came out at 3.6 gig. Very shortly thereafter, HBM3 was announced at 6.4. And then I have in this blue box, we have solutions now on the market, and Rambus has been leading the way. We had our first HBM3 came out at 8.4 gig, and that was in anticipation of the fact that the standards, these standards are not sitting still, that the customers need more and more bandwidth. And so right out of the gate, we said, 8.4 gig is going to give you now, a terabyte of performance, and that's really what we're seeing these generative AI needs in the processors, whether use one or two or four. So you can see you could very quickly get a significant amount of bandwidth performance. So that's kind of the raw standard, but let's look at what you can do in a system now. So you can see here what I've done is I've taken, typically you're going to have multiple HBM stacks, and I drew on if you're looking on the right side chart, that orange looking line that says, okay, that's kind of your magical 1 terabyte per second performance number. And now you can start to measure out in your systems how much, say I need a terabyte of performance, how many HBMs do I need? So with HBM2E technology, for example, you can take, if you look in the middle here, you can see 2 HBM2 stacks will get you up to 922 gigabytes per second, so very close to that performance line. Now with HBM3, two stacks will get you almost 1.4, 1.5 terabytes of performance. And then if you have in some of these higher performing systems now with 4 stacks, you can see even at the speeds of I just showed 8.4. These speeds, by the way, are based on a 6.4 design, which is the standard. But at 8.4 now, you can get 4 terabytes of performance with 4 HBM stacks. So this is a good way to start to evaluate how you want to provision your system. The other good thing about HBM is you get all this bandwidth in a very small footprint, and you also get very good power efficiency. So I wanted to show you an accelerator card that's out in the market that uses HBM. This is a company called Inflame, and they're building, you can see this Cloud Blazer card, and they've got a couple different versions of that. If you look at the picture, I like this one because the picture in the middle is very kind of informative from how HBM is built. So if you look at the SoC here in the middle, you've got your processor, and then around the edges, you can see there are 4 HBM stacks. And you got 2 on each side, and that processor in HBM then sits on a silicon interposer. So we've got you can see the 2.5 silicon interposer, and then that whole interposer sits in this package. So this is a nice way to deconstruct the HBM system. And so now with the accelerator card, you can configure it based on your processing requirements. So they have their T10 card that gives you 80 teraflops of performance, and that uses actually 2 HBM2s that gives you 512 gigabytes of memory bandwidth performance. You've got 16 gig of bits of memory storage at a 225 watt power card. If you go to their maximum card, you can see 256 teraflops of performance, so it's significant performance. That one uses 2 HBM2E cards and gives you 1.6 terabytes of performance and 32 gigabytes bits of density. And so you can imagine that this is the current generations of card. As we're moving into HBM3, you can see significant performance increases. And again, these accelerator cards, when you look at the data centers, the data centers are becoming much more, have to become more configurable to support these expanded workloads. And these type of accelerator cards help to do that. So let's continue to drill down and look under the hood of HBM. So on the right-hand side, I have a cross section of the HBM. The last picture was an actual chip and a deconstruction, as I called it. But here you can see the system from the side. So if you look, I'll start on the far right-hand side. You've got your system on a chip, and you can see that in blue here is the HBM memory subsystem. And I call it a subsystem because there's 2 components to it. It's the physical layer, or the PHY, and also you have a memory controller. And so Rambus provides the full subsystem, which combines the PHY plus the memory controller. And then you can see here that the PHY is connected through the silicon interposer. In this case, it's today most commonly used as silicon interposer, but there are other types of interposers that are starting to come out with redistribution layers. And but that's the topic for a different talk. So anyway, you can see that you can connect the system SoC to the DRAM through the interposer. And then this sits on a package substrate, more traditional package substrate, and then this substrate will sit on your PCB. So that's just to give you a look at the system. And you can see the DRAM here on the left-hand side. So you can see all these DRAM slices that are connected, these TSVs, through silicon vias, and that's connected through a logic layer and then out to the interposer. So that's why it's called the 2.5D system, because you actually have you've got a 2.5D connections, but then the DRAM is actually a 3D design. And from a subsystem standpoint, Rambus provides, as I mentioned, 8.4 gigabits per second per pin. That gives you a terabyte of performance. The PHY and controller is integrated. And one of the advantages of having an integrated PHY and controller is that we work closely with customers to make sure we optimize the bandwidth and we tune that for the specific application. Every single design has different requirements, and it's important to maximize your DRAM efficiency. And then the other advantages I already talked about was having the low power, and power management is pretty significant. So we look specifically at the physical layer, or the PHY. You can see here that the PHY connects directly to the DRAM. And there's a couple of key features that we haven't talked about. Certainly, it supports all the different stacks of DRAM stacks. But now you've got this closed, tight system, and you've got no way to look inside the interposer. So you need, for example, you have redundant lanes, you have lane repair. If a lane goes bad, you can remap that lane to there's redundant lanes that you could remap. And so you can do that in real time. There's also a IEEE test interface. You can get in there and do scan and look at what's going on. Rambus also offers a development environment called Lab Station that allows you to transfer data to the DRAM and allows a very powerful debugging environment. So even though you have this closed system, we still have ways to get in and start looking at and analyzing what's going on inside that 2.5D system. And then on the memory controller side, I just talked about it's configuring your controller to support the specific AI that you're trying to network that you're trying to optimize is very important. So the controller is configurable. It's soft IP, the physical edge hard IP. And you can pick the different blocks that you need for the controller. For example, if you need a read, modify, write core, you can pick the interface to your SoC. So if you have an AXI bus, for example, or if you want it multi-ported, or Rambus even has its own proprietary interface that can be used. And so this is very configurable. And also have a ECC block for a correction. And then based on those blocks, those light blue blocks are your configuration. We build that. And then we have test benches and tools that allows you to start running simulations through the controller to the DRAM. And we also have models for the PHY as well that allows you to start building and optimizing your system. And then once that's been optimized, then we can we'll basically take that optimized memory controller and PHY, and then we'll validate that and then deliver this whole all this blue as a complete memory subsystem. The last piece I wanted to talk about was the interposer design. So again, it's very key from us performance to optimize your interposer. And Rambus works very closely with our customers to provide a reference design. So it's a good starting point for the interposer. And you'll need to run simulations to try to get your cleanest eyes, most wide eye openings. We'll do all the signal integrity checks with the customer. And support you all the way through the design. And then I want to just very quickly show as we're moving into higher speed higher speed with HBM3, you're going up to 8.4 gig. You're going to need an interposer that has additional metal layers. So in HBM2E, typically you'd see 3 or 4 metal layers on the interposer. Now, as we go to HBM3, you'll see stacks that are going past 4 layers or greater, and this allows you then to route all those signals at much higher speeds. For example, getting better oxide thickness, a dielectric layer, even having capacitors inside the interposer. So again, as we're going to higher speed, we want to make sure that you can get that full performance out of the system. One of the key things about picking your HBM vendor is having that production experience. So you can see here, and I won't go through all the details on this slide, but Rambus there are many systems deployed with Rambus IP. We've worked with all the different foundries and we've all the different types of applications and customers. So if you can choose Rambus with high confidence, and we can bring that experience and help you to get your system built. So I just want to summarize that. So there's no end in sight for data growth. We see continuing to stress the infrastructure. We see the need for new custom processors, and these high performance accelerators are just going to need more and more memory bandwidth. So HBM gives you the best memory bandwidth today, and we're seeing the systems being built with multiple HBMs. And I'm sure that the industry is going to continue to push forward with higher and higher memory bandwidth performance. And then finally, Rambus offers a fully integrated system. So it's not just about the HBM PHY, it's about you have to have a good controller providing you the system design with the interposer and package. And we have a team that's provides outstanding support with all our history of signal integrity. So thank you for taking the time to listen in. There will be opportunities to ask questions, and or you can reach us at rambus.com. Thank you very much.